Hi, my name is Justine Harkness, and in this video we'll look at how to calculate the change in the electric potential energy of a system. We can derive the equation for electric potential energy by multiplying Coulomb's law by the distance. And this makes sense because the unit for electric potential energy is the joule, which breaks down to a Newton meter. Coulomb's law tells us the electrostatic force and distance would be, of course, in meters. So to get the equation for the electrostatic potential energy, we would have Coulomb's law, which is K Q1 Q2 over R squared, and we'd multiply by the distance R. And notice, when we look at our R's, the R in the numerator cancels out with one of the R's in the denominator, and that's where we get K Q1 Q2 over R for our electric potential energy. Now, as we saw in earlier videos, the signs of the charges become important. If I have like charges, such as a positive and a positive, well, if I multiply two positive numbers, I get a positive value. If I had two negative charges, if I multiply a negative number by another negative number, I also get a positive value. So for like charges, we will always see a positive energy value. On the other hand, if I have unlike charges, for example, a positive charge and a negative charge, when I multiply a positive by a negative, I get something that is negative. So unlike charges or opposite charges will always have a negative energy value. If we are looking for a change in the electric potential energy, well, if we're changing energy, we're looking at an initial and final potential energy. So the delta U would be equal to the final potential energy minus the initial potential energy. And let's take a look at some practice questions to apply this. This question asks us to compare the electrostatic change in energy and also the gravitational change in energy between a sodium cation and a chloride ion as they start 10 meters apart and then move together to a final distance of 0.236 nanometers. And then we're given some information about the mass, the charge, and the constants. Now let's start with the electric potential energy. There will be three parts to this. First of all, we'll have to choose the equation for electrostatic potential energy so we know what we need to plug in. And our equation for electric potential energy is KQQ over R. Now let's find the information we need in our question stem. So we have the charge of either +1 or -1 has a magnitude of 1.6 times 10 to the negative 19 coulombs. So that will be Q1 and Q2, of course, with the charge signs included. We also are given K, our value for K, of 8.99 times 10 to the 9, along with its units. And then we have our distances, 10 meters and 0.236 nanometers. So let's start with our final distance of 0.236 nanometers. Now, because our constant K is in the units of meters, we had to convert our distance also to meters. We plug in our value of K, we plug in the charges. Notice because I have a -1 charge, I also have a negative for the charge in my equation. And if we plug this into a calculator, we'll get -9.75 times 10 to the negative 19 joules. We can do the exact same thing with our 10 meters, or our initial value. It essentially becomes a plug and chug. Notice now instead we've plugged in 10 meters and we would get our energy at the end there. But we need to get our change. The change is equal to the final minus the initial. So we'll plug in our value for our final, we'll plug in our value for our initial and just calculate the difference. So our change in electrostatic potential energy would then be negative 9.75 times 10 to the negative 19 joules. Notice when we are calculating the change in electrostatic potential energy, our initial value, that negative 2.3 times 10 to the negative 29, is very, very small. This is similar to how at an infinite distance, the electric potential energy is zero. When we have a 10-meter distance between our two charges, that is really, really far away. So our initial potential energy is very, very close to zero. The fact that the change in electrostatic potential energy is negative makes sense. Remember that opposite charges have the lowest potential energy whenever they are closest together. So if I take a positive and negative charge and move them closer together, there should be a decrease in their potential energy. So now let's take a look at the gravitational change in energy. So we're going to go through the same process. We need to choose the equation for gravitational potential energy, calculate the potential energy at our two differences, and then calculate the change. So the formula for gravitational potential energy is negative G, and G is the constant. It is given in this question stem. We have our two masses. Notice that we are given the mass of sodium and the mass of chlorine in this question, and then over the radius. So we'll start with our final distance of 0.236 nanometers. Notice we also need to get that in meters because G is also in the units of meters. And then we'll plug in all of our values, and this will give us our final gravitational potential energy. Now, we're going to do the same thing for our initial gravitational potential energy, just plugging in 10 meters for the radius. And if we crunch the numbers, we would get our initial potential energy. To calculate the change of potential energy, we'll just take the final minus the initial, we'll plug in our values, and then we would get our change at the end. When we compare the change in gravitational potential energy to the change in electrostatic potential energy, we notice that the change in gravitational potential energy is significantly so much smaller than our change in electric potential energy. This is why whenever we're looking at chemical reactions, it really comes down to the reactions between charges, and we completely ignore any changes in gravitational potential energy. So now you should feel more comfortable calculating the change in potential energy.